Yeah, Kausal sir, are you there?
Yes, sir.
Okay, good afternoon, everyone. Uh, we are very delighted to have you on the platform of Association of Indian Physicists. And today, on behalf of Association of Indian Physicists and Janardhan Singh Foundation, I heartily welcome you all. And today's session will be chaired by Kausal sir, who is a research scholar and faculty in the Department of Physics, Baroda University. So without investing further time, I request Kausal sir to chair the session and introduce the speaker. Over to Kausal sir.
Thank you, sir. So, today's our guest and a very young and uh, enthusiastic scientist, we can say that, Dr. Binaya Kumar Sahu, and he is a assistant professor, higher education department, Department of Physics, Panchayat Degree College, Baragra, Odisha. In 2023, you completed your postdoctoral research at NICER Bhubaneswar. You were employed as a research scientist in NICER Bhubaneswar in 2022 on the spectroscopic and mass spectroscopic study of cancer scan project, which was sponsored by Canostic GmbH. In addition, you received your doctorate from the Indira Gandhi Center for Atomic Research in 2019 in the field of low dimension SnO2 growth and application. Your area of interest are designing a smart nano architectures and comprehending self architecture, metal oxide, metal sulfide, plasmonic metals, and graphene oxide nanostructure are used to study the optical, electronic, and magnetic characteristic of nanostructure. Many methods such as Raman, PL, UV visible, FTIR, XPS, EELS, Mossbauer, and so on. The author has published over 25 research papers in esteemed international journals and authored two chapters for books. Additionally, you have been honored by numerous institute for presenting a poster at conference, and in 2021 HBNI Mumbai bestow upon you the prestigious award of outstanding doctoral student. Additionally, you have succeeded in GATE and NET examination. You were awarded both UGC scholarship and ULM and AWA postdoctoral fellowship. So now I am now extending an invitation to Dr. Binay Kumar Sahu for fascinating lecture on architecting a nano world using a metal oxide and sub-wavelength metal nanostructure for energy and environmental application. Please, sir.
Yeah, thank you, Kosal sir, and good evening to all. So, can I share my slide now? Because I am not allowed yet. Yeah.
Just please share your.
Yes, sir, please.
Yeah, is it visible? The first slide of my
Yes,
presentation,
yes, yes,
Yes,
sir.
sir. Yes,
and it's moving, right?
Yes, yes, yes.
yes. Yes.
Okay. Yeah. So good afternoon to all. First of all, thank you to Association of Indian Physicists, and I would like to congratulate all the active member. And I'm really appreciating their hard work for like starting a new area, now, especially in the field of physics in India. And especially its aim is to connect the small university and colleges and to give the fragment of physics. And hopefully, most of the students, like those who are not connected directly to IIT or some big institute. So it's they are giving a very strong message what is really required for our education system. That education doesn't lie in the very big institute or very big instruments and all. What we need is a strong willpower and the interest. If you are strongly motivated, strongly interested, then nothing is far beyond uh, to get your success. And of course, this AIP is working as a wonderful bridge for all the students to get to give this fragrance and to give the flavor of physics. So especially I would like to congratulate all the active members, especially Sanjay sir and Captain sir. And again, I would like to thanks to give me this wonderful opportunity to present my work. So this is again already sir has introduced me. So this is Dr. Binaya Kumar Sahu. Currently, I'm working as assistant professor in Department of Physics, Panchayat College. So the title of my talk for today is Architecting a Nano World using metal oxides and software plane metal nanostructures for energy and environmental applications. So basically, the metal oxide, what I'm going to talk about is already sir was talking. It's tin oxide. It's a important metal oxides and its various application, especially in the reference to energy and environment. Energy like supercapacitor and all. Environments means especially I'll be talking about environmental monitoring, sensing application, and few other application I'll just project, but I may not show due to the lack of time. And the metal we people have heard about different ages like stone age, then iron age and bronze age, and all the ages passed, and still why we are talking about the metal. We'll be talking about a very special metal, and that is plasmonic materials and their application. So that related thing we are going to study. So let me introduce my material, that is tin oxide. Basically, it's a wide bandgap material with a bandgap of 3.6 electron volt. Uh, Hello?
Yes, sir, you are
Hello?
Yeah,
audible.
Yes.
we can.
It's audible, right?
Yeah, yeah,
Yes.
sure.
Yeah, sorry. Yeah. So, yeah, what I was telling, it's a tin oxide is a wide bandgap material. So the bandgap is around 3.6 electron volt. And if you see the Bohr excitation radius is 2.7 nanometer. What is this Bohr excitation radius? This is a very important concept. Like we have seen in quantum mechanics and classical mechanics, there are two different design. And quantum mechanics is basically very interesting because of its special effect on the material property. So when a material will start showing the quantum property, when the size of the materials will come down to the Bohr excitation radius, and that is different for different material. And whereas for tin oxide, the size is around 2.7 nanometer. So by any means, if you are able to make some tin oxide, the size below than 2.7 nanometer, then that will start showing very different properties as compared to the bulk, and that will be exploiting for various applications. And what makes this material more interesting is the presence of defect. Generally, whenever you heard the word defect, that give a negative impression, or defect is not good. But for our material, for a material like tin oxides, defect is very good. As I explained, this is a wide bandgap material, and here you can see, like if you see these two things, this is they don't present in general, and the difference like from here to here, this is the actual bandgap of the tin oxide. But whenever there is some kind of defect, especially there the oxygen vacancy. So what is that oxygen vacancy? Here we can see the structure. This is the structure for the tin oxide. Generally in tin oxide, what happens? It's of course it consists of tin and oxygen, and one tin is surrounded by six oxygen, six different oxygen, and their position is very much fixed. Like here we can see this is a plane and this is a plane, and few oxygen are bridging these two planes. So these oxygen that is bridging these two planes are known as the bridging oxygen, whereas the oxygen lying over the plane here, they are known as the in plane oxygen. But by any means, if you are removing them, like if you are removing this oxygen or this oxygen, they will create certain kind of oxygen vacancy. And because of the oxygen vacancy, certain energy state will be created below the conduction band. And we are very familiar with this kind of structure. If you are creating some kind of donor state closer to the conduction band, they behave as a N-type semiconductor. So earlier, the band gap was 3.6, what is a wide band gap material. But with the inclusion of the oxygen vacancy, what you are doing, you are converting your material into a N-type semiconductor. And whenever I am using the word semiconductor, various application will come into my minds. Like it can be work as the like waveguide, memory device, especially this memory device, solar cell, photo detectors, photocatalysis. All the application will be coming whenever you are having a N-type semiconductor. Then the question is that how I'm going to identify or how I'm going to calculate this defect or this oxygen vacancy, how much oxygen vacancy are there and where they are located and how they are affecting the band structure. Those are the crucial thing I should know before I'm going for various applications. For that, what I have to have a concrete knowledge on the spectroscopic technique. There are various spectroscopic techniques like Raman, PL stand for photoluminescence, then Fourier transform infrared spectroscopy, XAS, it's X-ray absorption spectroscopy, Mossbauer, lifetime measurement. I may not talk about all the spectroscopic technique to scrutinize the defect in my material, but I'll be talking various various techniques, especially I will be talking about the photoluminescence, this lifetime measurement, UV visible, Raman, all this spectroscopy I'll be talking about. And today I have chosen three special directions or three special sections by utilizing this tin oxide for various applications. The first one will go for optical detection of the ammonia by deciphering the blue luminescence emission mechanism in the tin oxide quantum dots. Like we'll take some tin oxide quantum dots and we'll see how the photoluminescence property or how the luminescence property is going to change in the presence of ammonia. And by doing that, can we develop some sort of sensor? Like because I want to sense the ammonia. So can I make an optical sensor where the optical activities or the luminescence properties of my material will be changing in the presence of ammonia. So that is the first section what will be deciphering. And the second, like coming to the next section, again, we'll take the help of the photoluminescence to make some waveguide. And of course, whenever I'm telling the waveguide is kind of a longitudinal structure, or it's a one-dimensional structure where light has to pass. And it is very much important for the communication sector. But again, our aim is to make the instrument small. So I want to miniaturize my device. So we'll be talking in the nano region. So basically, I want to make a nano-sized waveguide to transform my data. And with the upcoming slides, we'll see whether we'll be able to make that or not. And finally, if time permits, as I told, we'll be talking about some soft wavelength, spatial metal, and of course, again, we'll add some magnetic properties to that metal for various applications. That application includes like trace detection of few dyes and catalysis. So this is the optional section what I've kept. If time permits, I will go there. With that, let's start our first section. As I explained, the title of the first section will be the optical detection of ammonia by deciphering the blue photoluminescence emission mechanism in tin oxide quantum dots. And this is like I have kept it chapter 1, not inspired from any book, but inspired by some movie. Like all of us are very fan of movie like KGF, right? So they are also having this chapter 1, chapter 2. So in that way, I have kept the name. It is chapter 1. And being a movie lover, this word is very much well acquainted to us. What we call generally light, camera, and action. But again, we are physicists, so we don't believe in this light, camera, and action. Rather than what we tell, it's laser, spectroscopy, and action. Or you can read it as the application. So basically, what's our plan? We'll take some material, we'll shine some laser on that, and we'll make some spectroscopic experimentation on that, and we'll see what kind of application it can be done on that particular material. So outline of the talks goes like this. Here we'll compare the well-equipped resistive sensing with the optical sensing. That I will explain what is a resistive sensing basically. Then again, I will be explaining what is a PL and PL-based sensing, then the sensing mechanism and the conclusion. So let's start our journey. So it goes like this. So let me give a very brief introduction about the resistive sensing and how it works and why it is important. Most of us have heard about the hazardous incident that happened in the Bhopal, because some kind of toxic gas came out from that industry and that killed numerous, like lots of people were hampered by that. So to avoid such kind of situation, what should have is a gas sensor. Basically, we should have a sensor that will sense the gas. If some gas is leaking or something, that will give some signal. And this is resistive sensing is well utilized in various industry. Generally, what happens in a resistive sensing, if some sort of gas is coming, the resistance of that particular material will be decreasing. From that, you can tell, okay, there is some gas is leaking. So how it works basically, let me explain you. We have certain kind of material. This is a material, and these are the oxygen. Like if you keep your material, that will be absorbed by the oxygen. That is that process is known as physiosort. In that process, what will happen during the absorption? It will take out few of the electron from your material. So there will be a deficiency of the electron in your material. And if there is a deficiency of the electron, then what we can tell, the resistance has been increased. If there is no electron, there is no charge carrier. So it will possess a very high resistance. But subsequently, what will happen if you are giving some gas like ammonia, or sorry, if you are giving some gas like methane or something, that will go and react with this oxygen. Okay, and they will take out this oxygen from the surface, and the trapped electron will be released back. And what will happen in that process? The resistance will decrease. So basically, what will happen if you have some kind of material, and if you are giving some gas, basically what will happen? The resistance will decrease, and from that you can tell, okay, there is some gas. Like if you'll see, this is a typical plot for the gas sensing mechanism. This is the resistance, and then the presence of, this is the example for the methane. Basically, the resistance is decreasing. Okay. Again, you are like closing the gas, so again the resistance will increase. Again, we will flow the gas, again the resistance will decrease. And this has been done in different concentration of the gas. So you can see, if it is a higher concentration of the gas, it will reduce more, like the resistance will come down to a higher extent. For the lesser concentration, it will come to the lesser extent. So this is a very well-established technique. Then why we are bothering about a new technique? Why you want to spend some more money or some like research you want to do for the new technique? Because this technique has some shortcoming. All the experiment, like the chemical interaction, what I told, generally that happen in the high temperature. Like at least it should be 150 or 200 or 300. So for that, you need an extra setup, and that is what we don't want. And basically, to have this, you have to have a complex structure and device fabrication. And as I told, it's a resistive switching. So the resistance need to be monitored always. So what you need, it's a external electronic complication may come, and contact problem. This is a very serious problem. Like who are working in electronics, they will like agree with me. Whenever you are making some device, whenever you are like measuring some electronics property, this contact problem is a very serious problem, and limited selectivity. As I told, if I am giving the methane, the resistance is decreasing. If I am giving the ammonia, the resistance will behave in a certain way. So how will identify whether it's a methane, ammonia, or ethanol, methanol, or what kind of gas you are dealing? So that is the problem known as the limited in the selectivity. So to tackle this, we have to have a very special technique that is known as the optical sensing. So the previous one, we can tell it's a electrical noise because the resistance is changing, and by seeing the electronics property. So I generally referred it, generally the scientists, the research people referred it as a electrical noise. But now we need a different set of sensing mechanism, where what will happen, generally the optical property will change. Optical property like luminescence, like let's not talk about these two things. We'll prioritize on this property. The luminescence properties of a particular material, how it is changing in the presence of a foreign gas, that will come under the optical sensing. And exactly complementary to this technique, these are the benefits over the optical sensing, and what we call it as a optical eye. So basically, this kind of sensor may work in the low temperature. There is no contact problem because you are not going to measure any electrical signal from that. And here you are having various like parameter to measure. Like you can see the intensity of the optical signal, the wavelength, how the polarization is changing. Based on that, you can tell that you can measure the sensing mechanism. And one of the good thing is that remote sensing, because there is no contact problem, then you can remotely sense your object or your things, and there is no electromagnetic disturbance, of course, and privilege of selectivity. That will be seen in the upcoming slides, how the optical activity is changing differently in the presence of different kind of different kind of gases. And of course, it is having various application, like in the environmental gas analysis, automobile industry, chemical industry, in medical application. And recently I have added this particular segments, this space exploration, after our success of the Chandrayaan. So I am becoming a little bit over ambitious. Okay, we can make this kind of optical sensor in the space exploration. So with that idea, let me show you the trailer, because as I told, this is the chapter 1 KGF, so I'm connecting with the movie style of structure. So this is the trailer, and of course I'm not expecting all of you to understand this figure, because we don't understand many of the things from the trailer, so that's completely fine. But from here, that enthusiasm or something we should get, something we should be understanding, so that you can enjoy the movie. So basically what we are doing here, here we have we have made one instrument. This is the instrument, and here we are keeping our material, that is tin oxide, of course, and we'll take the PL spectroscopy of that material. Okay, and later on what we'll do, we'll again measure the PL in the presence of different gas like ammonia, methane, oxygen, and different NOx gas. Okay, and we'll be seeing how the PL is changing in the presence of different kind of gas. So that is basically the key structure, a key idea of this particular work. So this is okay. Just those who don't know about the PL, just think this is some random line. And those who knows about the PL, I'll give a brief idea what is happening here. This is the PL spectra. Okay, here we can see this is a luminescence spectra from the tin oxide, and this is this is pretty much clear. But when you are giving different concentration of the ammonia, like 32, 64, 188, and 256, you can see there is certain changes in this region. And especially this region, 2.77 and 2.96, if you will convert them in wavelength scale, they will come in the blue region. So you can see in the presence of ammonia, there is an increment in the PL spectra in the blue region. Okay, so that is the trailer. You just then we'll see how all the things are happening. Okay, and this is some weird theoretical things that theoretical people do that I also don't understand much, but we should be grateful to them, because of them we understand the actual physics. So that also will be talking slowly, like what is these two structure. And whenever you are making some movie, what is our biggest dream should be that movie should got some award. It may be some Oscar award or something. So that way, I will see how this particular thing is also connected to this work. That there is something called as the Distinguished Students Award. Okay, so we'll see how this work was related to that particular award. Okay, so with that, let's go and let's explore the PL. Okay, how so those who don't know about the PL, let me explain you what is a PL spectra. So as you know, already I have explained, tin oxide is a wide bandgap semiconductor. So it's a semiconductor, so it should be having a valence band as well as a conduction band. So this is the valence band and this is the conduction band. So when light shine on that, or laser shine on that, what will happen? The obvious thing will happen is that one hole will be created and one electron will be created, and the electron will go here and a hole will be remaining here. And in the subsequent time, what will happen? The electron will come back and that will recombine with that particular hole. And that process will give you the luminescence property. So in principle, what will happen? If the band gap is around 3.6 electron volt, I should get a spectra, or I should get a peak around 3.6 electron volt. And this is the typical spectra of the tin oxide. But you can clearly see there is no peak. Here there is no humps or no peaks around 3.6. Why so? Because this transition is not allowed for tin oxide because of the dipole forbidden rule. Those who have studied this perturbation theory in quantum mechanics, they can go and check. There's something called as the dipole forbidden rule. And because of that, for tin oxide, this transition is not allowed. Then why we are getting all the peak around 2.0 and all? Because of the, again, we need to be thankful to the PL spectra, to the defect or the oxygen vacancy. Generally, as I have shown, this is a defective tin oxide. Okay, and here some vacancies are there, means this oxygen are not present here, so they are creating some sort of oxygen vacancy. And because of the oxygen vacancy, some additional state will be created close to the conduction band. So now what will happen? My electron will go here and it will come back here, and from here to here it will transit, or it will come here and it will show the transition, or it will show a recombination. So instead of 3.6, I'll get a peak around 2.1 electron volt and all. But here, if you will see, there is some small peak is coming up around 2.75 and 2.96. So basically, why these two peaks are coming? So that is a very interesting thing. Then I searched few of the paper, and I did my research. I did some literature survey. What they explained, again, these defects are not safe. And here comes the importance of the nanotechnology and nanomaterials. If you are dealing with a bulk material, they show different kind of defect. They are known as the bulk defect. But if you are dealing with a nanomaterial, a small material where the surface is very high, the surface defect will create a very different state. And this particular state. You can see this particular state comes due to the surface defect. And this one, this like here, these two are similar structure. Because of the surface oxygen defect, you can get this state. So what will happen? The electron will go here, and from here to here, it will show the transition. And this transition is this one, this 2.77 and 2.96. This is what various paper they claim. Because of this thing, this is in the surface side, the oxygen is not there, so they are creating some sort of energy level above the valence band, and this particular energy state will be reflecting here. Okay, then the question is that how will we distinguishing this defect and this defect? Some defect is coming from, like, some recombination is happening from here to here, and some is happening from here to here. So how will distinguish between this and this? So there is, again, I saw some paper, and they have given a special technique that is from the lifetime measurement. What is told, the lifetime measurement for this kind of transition is very high, whereas the lifetime for this transition is very less. So what is, again, the question is, what is lifetime? Lifetime is a very simple thing. Like the electron is going here and it got trapped, like it rested here for some time before it saw the transition. So that rest time is known as the lifetime. So how much time it rests here before showing the transition, that particular thing is known as the lifetime. So what they told, the surface defect show higher lifetime. This is the point I want you to remember. The surface defect show higher lifetime, whereas the bulk defect shows the lesser lifetime. So what is the then we are telling that is the surface structure and surface defect. And how can we prove that surface structure? There is one more technique that is known as the XAS. It is known as the X-ray absorption study. Without going to the technicalities and without going to the very important and very enriched physics, what I will tell, if you do the X-ray spectra of your material, and if you can see this kind of peak, like this is the comparison between two peaks, there's a peak you can see. If this peak is there, you can tell that it contains lots of surface defect. And if it is not there, so it doesn't contain much surface defect. So here I want to take you two important keynote advice or keynote summary. One is that this 2.77, that is related to your surface defect. Okay, and the lifetime for the surface defect is more. And if surface defect is there, we should be able to see this kind of peak. So this is the flashback. This is the flashback, or this is the prerequisite knowledge we should have before going to prepare our material. So with this knowledge, let's go and let's prepare our material. So let's welcome our hero to the movie. As I told, this is the tin oxide, and we didn't go for very complicated and very costly technique. We took very simple chemical route. We basically added ammonium hydroxide with the stannic chloride, and what we obtained is the tin oxide quantum dot. Why I'm telling this quantum dot again? Because the size is 2.3 nanometer. As the introductory trial, as I was telling, if it is less than 2.7 nanometer, then it can be acted as the quantum dot. And again, like those who are well acquainted with the experimental thing, they can enjoy the slides. Other, you just for the time being, we can have we can see the actual result and the interesting part. This is not very interesting. These are the XRD, basically the quantum dots XRD, and these are the Sahu structure. Like this quantum dot were again annealed at the 800 degrees Celsius to make the bigger particle. They are of the 25 nanometer size. So this is the XRD of the bigger particle, and this is the XRD of the smaller particle. And these are the Raman spectra. These are the FTIR spectra, and this is my PL data. Like this is the PL data that I have taken from my material, and this is exactly same what other experimentalists have proposed. Like you will get a peak around 2.0, and there will be a small hibernate or a small hidden peak around 2.77 and 2.96. Yeah, so this is 2.77 and 2.96. And as I told, this is a quantum dot. So this red color data is coming from the quantum dot. And we could see 2.77 and 2.96 for the quantum dot, whereas that is absent for the bigger particle. As I was telling the whole story, like if you are coming to the smaller region of the nanomaterials, the surface defect will be more. And that's the reason we are getting a 2.77 and 2.96 for this material, whereas that is absent for the quantum dots. And like the previous assumption, like they have shown some big data, but why to believe them? Because being an experimentalist, being a physicist, the first thing what you should do is that don't believe anything unless and until you have observed it, you have seen that. So carried out the similar experiment. This is the lifetime measurement. Okay, and what we saw this 2.77, as I told, this 2.77. This is the transition related to the surface defect. They show a higher lifetime. The lifetime was around 87.3 or nearly 90 nanosecond, whereas for the bulk defect, it is around 4.7 nanometers. So our first, that's why I was asking you to kind enough and remember that two particular thing. First one is lifetime because of related to the surface defect, it is 2.77, then lifetime is high. So whatever they have assumed or whatever they have proposed, they were exactly correct. And the second thing what I was telling about the XAS absorption, and here we can see like S1 stand for the 100 degree or the smaller particle, the fast particle, and 8 stand for the 800 degree or 25 nanometer particle. Here we can see, we could see a pre-H spectra over here. So this is the pre-H spectra. So that confirms the surface oxygen vacancy is very high for the quantum dots. And this is the unified band structure what I have, like what our group have proposed for the PL spectra. So if you don't understand whatever I have taught, like whatever I have till now, don't worry. If you remember this diagram, everything is fine. Okay, so let me summarize whatever we have studied or whatever we have discussed yet. Like this is the tin oxide. There's a conduction band and a valence band. If you sign some laser, one hole and one electron will be created. And this particular electron will never come back to the valence band because of the dipole forbidden rule. However, this electron can go here and this will come here. So we can get some peak in 2.45, 2.28, 2.11, 1.96 and 1.85 and all this thing. But there are two peaks, this 2.77 and 2.96. Generally, they are very much, like their intensity is very much less in the whole spectra because there is a defect, surface defect lying at the surface. They are because of this SN4 side, because oxygen is because of this SN4 side, the electron will come here and they will be trapped here. So we cannot see it like this 2.77 and 2.96. That intensity is very much less. So if you understand this much, that is fine. So let's start our final battle. Like it's we are coming towards the climax of the movie. Generally, in climax, what happens? There will be a tussle. There is a battle between our hero and the villain. So here our villain is of course ammonia because we don't want ammonia in our environment, and our hero has to fight against the ammonia to show some gigantic property. So this is the experimental setup what already I have explained. This is the stage where the material like tin oxide will be kept, and here the ammonia will be passed through. And as I have told, like now more or less you people have some idea about the PL spectra. So this is a PL of the tin oxide when there is no ammonia. But when you are giving the ammonia, slowly these two mysterious peak, basically this 2.77 and 2.96, they started enhancing. Okay, so later on we'll see why these two particular peak are so kind that they are their intensity is basically increasing in the presence of ammonia, whereas the other peak like 1.86, 1.85 and 1.96 and 2.11, they are remaining silent. So that part we'll be seeing. Okay, so this is the sensing data basically. And being a like sensor specialist, those who are working in the field of sensor, they know like whenever you are doing some sensing study, one most important thing is selectivity. Like you need to be very specific that your material should not show the similar property in the presence of other gases. So we continue the same experiment in the presence of various VOC, and here we don't see any increment in the blue, like this 2.77 and 2.96. Here, what exactly is happening? The whole intensity is coming down. So we can tell that your material is very much selective towards the ammonia. So whenever ammonia is there, the PL spectra will behave very differently as compared to the other. Okay. So this is the final battle. Still, it is continuing. Okay. And as I was telling, if you are working in the sensor field, one of the important factor what you should see is the sensitivity. Okay. So this is the sensitivity. Here, what you can tell or what you can conclude how a particular peak is behaving or changing in the presence of gas and how it was before in the presence of gas. So this I dot is the intensity in the absence of the gas, and I gas is the intensity in the presence of the gas. So you have to do a little calculation, and this kind of spectra you can get, and you can see the 2.96 and 2.77. This related peak have enhanced very highly or very effectively as compared to the other peak. Here you can see the other peaks are remain silent, but the other two peaks they have seen a exponential growth, or they have increased a very uh, like they have increased drastically in the presence of various concentration of the ammonia. And what is the third parameter when you are doing the sensing study? That is the recovery. Like after interaction with the ammonia, like the once the interaction is over, when you are removing out the ammonia, how you are removing out the ammonia? Basically, we are using some inert gas, nitrogen and all. So they were removing your ammonia out from that chamber, and your sensor should go back to the normal condition. This is the intensity of a particular peak, this 2.96 and 2.77. Again, it's coming down to a original state. So it's show a better recovery. Then the question is that why this is happening? Because we are not just like we are not the engineer people, right? We understand physics. So why these particular peaks are enhancing? So those kind of thing, again, that came as a challenge and we need to solve that. And already I have explained you the very basic property of the sensing mechanism, right? How the sensor works. As I have told that this is the material, suppose this is our tin oxide, it contains lots of electrons, some oxygen came out, oxygen came, they interacted, and they got absorbed on the surface. So they are taking out of the electron from the system. And in the presence of ammonia, the electron are going back. Okay. But here the problem is that if the electron are going back, the PL should increase. Okay, because the electrons are the important factor. They decide the intensity of the PL. So if this is the mechanism, if I believe this mechanism is true, then what should happen? Once this become free to participate in the PL. If this is true, what is the problem? Like the bigger particle, this 25 nanometer particle, they also contain lots of oxygen vacancy. Okay, and they also should show some sort of increment in the blue region, but that is what is not happening. So this behavior is very specific towards the smaller material, but this never happened for the bigger material. So I have to turn down this mechanism. This mechanism is not correct, because if this is true, if this mechanism were true, then I should see a PL spectra enhancement in the blue region for the 25 nanometer particle also. But that is what is not happening. So I cannot believe this mechanism. So we came across one more proposition, that is the Lewis acid base interaction. So as I have explained, the surface contain lots of SN4 plus bond. Okay, and they can accept electron. And ammonia is kind of a base. That acts as a Lewis base, because they are having this lone pair electron over it, and they can give electron to the system when they will interact with the SN4 plus. And that is what you can clearly see. These are the TDP. This is TDP means the thermal desorption program. From here, what you can find out the active side on a particular material. So this 100 degree means these are the smaller material, then it is the next smaller material, this is the next, and this is the bigger material. So when the material is small, what you can see, the active side are high, whereas for the bigger material, the active side is not very high, and that is what is clearly reflecting in your PL spectra. So if you are dealing with the quantum dots of the smaller material, they show this kind of enhancement, whereas the the bigger particle, they don't interact with the ammonia. So this conclude this work with the revelation of the truth and a happy ending. So this is the final mechanism what we have proposed. So what is the mechanism? As I told, this 2.77 and 2.96, they were not very strong in the absence of ammonia, because all the electron were going this side to the surface side, the surface trough side. Whereas if there is a ammonia, what will come? This ammonia will come and that will scavenge, or that will occupy this particular SN4 side. So this electron cannot go here. this electron is no, because this side are no longer available for this electron to go this side. So where they had to go, they will come this side, 2.77 and 2.96. So in the presence of ammonia, what you will see this kind of enhancement in these two particular peak, this 2.77 and 2.96, and obviously they stand for the blue color. Okay, so that is the final truth. That is the end of this particular story. But again, there is a little confusion because on the surface you are having both SN4 site and SN2 plus site. So how do I confirm that this is ammonia is interacting with SN4 and it is not interacting with the SN2 plus? So with, to reveal that, again, we took the help of some brilliant theoretician, and they give this model. Like they did this competition between this SN2 plus and 4 plus. What they could find that the interaction is always with the SN4 plus and it was not interacting with the SN2 plus. This is the charge transfer basically. The charge transfer is happening at the SN4 plus site. So this is the happy ending things. Like if you are having a bigger particle, that will never interact with the ammonia. And if you are having a quantum dot or smaller particle size, if they interact with the ammonia, the color will turn into blue. Okay, pictorially. And this you can monitor using your PL spectra. This particular blue region will enhance in the presence of ammonia, whereas no such enhancement will be seen for the bigger particle. And here comes the like Oscar award kind of thing just for this thing. This work actually like a group we presented for APS March meeting. That's a very prestigious forum, and it's the information what also I want to convey, like who are in the master or doing PhD, they can write a like they can show their work, and there is a good opportunity to present your work over there, and you can interact with some brilliant people. So we presented this work, and for that, this work was awarded as the Distinguished Student Award for the year of March for March 2020. So this is the group of people like from different part of the world. They also like for their work they got this, and our work also was acknowledged there. So that is the happy ending of this work. Hello.
Yes, we can hear.
Yeah. So with this, our chapter 1 is over. So in chapter 1, what happened, I don't recall in KGF. I guess KGF you people might have seen, right? The Rocky White. So again, he will come back in the second chapter. Okay. So this is the second chapter, and this is a short chapter, of course. This is not going to take much time because already we know how Rocky White or how the tin oxide behave. Okay. So more or less we know about tin oxide. So I'll be showing the application chapter directly. Okay. So here we'll be seeing the importance of the photoluminescence in 1D nanostructure for waveguide application. Again, here go again, like before every movie, we have to say actually laser, spectroscopy, and X-ray. So we'll see how we'll sign laser and how we'll take the help of the spectroscopy and what sort of application will be availing using the 1D SnO2 nanostructure. So here we'll be using some waveguide technique, and previously we used a simple chemical synthesis. So and here, as you know, this KGF2 also the budget was bit more. So for this project also we had a big budget, like comparative to the first one. So we went to a better synthesis technique, that is the CVD, chemical vapor deposition, that I'll be explaining. What is this chemical vapor deposition and how do you use this PL for the waveguide property. Anyhow, waveguide is a building block in the photonic circuit. All of us must know that. And what is photonic? Photonic is the optical analog to the electronics, and that's really required for the miniaturization of the device, because whenever you are transferring your data through a wire, right, generally different kind of metal nanowire we are using, the main problem what we are facing is the scattering of the electron, and that will slow down your process. We cannot send your data very quickly. And if you want to send your data quickly, what you have to have that very well-known technique that is known as the optical fiber. And there comes the importance of the photonic circuit, and there the silver the metallic wire has to be replaced by something known as the waveguide. So waveguide basically will guide the light, and that will connect from one place to another place. And that will, of course, that is why I'm interested in the miniaturization. So we have to make some 1D nanostructure in the nanoscale. And where again we have chosen tin oxide because of its inherent one-dimensionality, profound optical properties, because last few minutes we are talking about the excellent optical properties of the tin oxide only. and low surface roughness, that also I'll show where the surface roughness we measured and how it is really low, and the refractive index. Because all of us know the basic principle of the optical fiber that worked on the principle of the total internal reflection. And for that, the refractive index is a very important parameter. And so to understand this, for the first step, what we have to do, we have to synthesize our material. So what I can tell, revert of our hero. So in the first cases, it was a quantum dots, but now it came with the more power and more elegance and more style. So now it is in the form of the 1D structure, 1D form. And how we made our material using the chemical vapor deposition technique. Here what happens, generally you take your material and you have to give certain temperature. Okay, this is the technique. And if you can, like I can explain from here, we generally mix this tin oxide and carbon, and we give a elevated temperature, generally 950 degree and 1000 degree. Then they will convert into gaseous form. Okay, and they will convert into SnO, and this SnO will go, and here we'll keep some substrate. Like this is our starting material, SnO2 and carbon, and we are giving some temperature, and they will go like this, and they will be collected over here on the silicon substrate. And on that silicon substrate, prior to this, we have already kept some catalysis. Catalysis, what is that catalysis? They are nothing but the gold nanoparticles. They basically will absorb this particular thing, SnO. Okay, and this SnO will combine to give the tin here. And we can see a unidirectional growth of the tin oxide nanowire. So this is the basic phenomena happens in the CVD growth. This technique is also known as actually VLS technique. VLS is nothing but your vapor, liquid, and solid technique. Why we are telling this a vapor, liquid, solid technique? Because our starting material was this gas. This was a gas. So SnO gas will come here and it will absorb on the liquid. This SnO, because of the higher temperature, this will be in the liquid form. So SnO will come and they will collect it here. So now that is in the liquid form, and slowly they will solidify and they will increase in the one-dimensional growth. So that is the reason this technique is also known as the vapor, liquid, solid growth technique. And what we did like this experiment in two different environments. First one is the 950 degree and second one is the 1000 degree. As I told, like our material need to be evolved and it need to be collected at certain temperature. This 950 and 1000 degrees Celsius. But the question may be coming, this is 50 degrees Celsius. What kind of change you are expecting? But no, there is a very drastic change and very beautiful change over the structure of the nanowire. This is the FESEM images of the, again, you can see the scale. So this is around 200 nanometer scale actually. So this, you can see this is little bigger. And what important thing you can see, this is of the square cross section, whereas this is the circular cross section. Okay. And again, we did like how you know that this is tin oxide. So basically we did some Raman spectra. Raman spectra is kind of, you can think that's kind of the fingerprint of the material. So this particular peak are coming, then you can confirm, okay, my material is formed. So from there we can explain this is tin oxide. And the beautiful thing, what you can see, they are really flexible actually. It happened accidentally, like when we were sorting out few of the sample from the silicon, we could see they are really flexible. You can see a knot over here. And we also did, like as I was claiming the surface smoothness and all, we did also few AFM, and this is a very special technique known as the KPFM, Kelvin probe force microscopy. Again, I'm just giving, I will not go in detail. From there, what you can do, you can see the surface potential of that material, and they are also very much uniform. Then the question is come again, as I told, we are not engineer, we are the physicist. So we have to understand the basic science behind it. Why this 50-degree change of the temperature making our material so different? Like some of is giving this square cross section and few is giving this cylindrical cross section. For that, again, we have to take the help of the thermodynamics, because thermodynamics always talks about the minimization of the energy. And what kind of energy? This is the Gibbs free energy. So we calculate the Gibbs free energy for these two particular structure. Here we can see, here I have written R1 square L1. This is the surface area. Sorry, this is the volume, right? For the square cross section. This is R1, this is R1. So this is R1 square and the length is L1. So this is the Gibbs free energy, total Gibbs free energy I have calculated for the square cross section. Where else here you can see this is the cross section is pi r square and the length is L1. So the volume is pi r square L2. Again, this is the surface area, and here also it is the surface area. And this is the energy per unit surface area. So we did a simple calculation using the thermodynamics, and we did the maximum minima calculation, because anyhow we have to see the energy minimization. And what we find after doing little calculation, that this 1950 degrees Celsius is always favorable for this kind of structure. Like the energy minimization will only happen if there is a square cross section for 950 degrees Celsius, whereas the cylindrical cross section is favorable at the 1000 degrees Celsius. So this is the basic physics behind the alternation of the structure. Basically, the Gibbs free energy is acting as a competitive phase during the nucleation, and we are getting two different kind of nanostructure. And now comes the action part or the application part. What we have seen, like we kept our material under certain laser and we are shining it. Why could here the laser was shined, okay, and the laser was moving. The laser was guided all over this lane, and it's coming out over there. You can see here there is a very small line is coming out. Light is coming out over here. Whereas you are shining light here, it is coming out this side. Okay, so if we are shining light here, and it is coming this side. So basically, our material is working as a PL-induced waveguide. That's a very important thing. This is not a normal waveguide. In normal waveguide, what will happen? You are shining a light here, and that particular wavelength will be transferring to this side. But here, what we are doing, we are shining with a light of 325 nanometer, because that generally looks, what is the color of 325? That generally looks blue. Okay, but here blue color is not going out. Rather, a yellow color is going out, because when you are shining with a laser light, it is creating some photoluminescence, and that photoluminescence color is yellow, and that yellow color is propagating this side. Okay, so that is why this is not a normal waveguide. This is the PL induced waveguide. So this is all about the second chapter. Basically, what we did, we made a 1D nanostructure using the chemical vapor deposition. We understand its optical property. We did some measurement for its surface smoothness and its inherent 1D structure. We understand the thermodynamics behind it, like why few of them were square and why few of them were in the circular shape. And finally, we have demonstrated their waveguide property by exploiting the total internal reflection. This is what I forgot to mention here. Why it is happening? Because of the total internal reflection. And here one more point I want to mention. There is something called as the critical length. The size of the nanowire should be more than that, like those who have studied like the electrodynamics chapter from the Griffith. Okay, so these two formula we have taken directly from the Griffith. We have calculated the critical length for the waveguide for this circular and as well as the square cross section using the Griffith formula. And we could see that the critical size was well, they were quite matching with our nanostructure that we have created. That's why we could see this waveguide structure or waveguide process was possible because of this critical length, critical radius, and that is the formula we have taken it from our textbook Griffith. Okay. So with that, actually, there are also various other things we try to make using tin oxide. Like we have created, we have also made some graphene oxide and tin oxide for supercapacitor application. As I was mentioning in the very beginning, we are also working the environmental application. So very dye degradation like methylene blue, and now also we are working the CO2 reduction and hydrogen, CO2 reduction kind of thing using this tin oxide, especially and other oxides. And room temperature resistive sensing also we have prepared. So these are the various spectrum of the we are working to make a nano world made up of tin oxide. And what I presented today is basically these two things: this room temperature PL-based ammonia sensing and Lewis acid-base interaction that basically they decipher the mechanism. And second one more aspect I explained, the waveguide behavior of the one-dimensional nanostructure. So, sir, do I have any the time is over, or sometimes I can present now?
Yeah, you can proceed, sir. You can proceed.
Okay. Yeah. Thank you, sir. Okay. So, yeah. So, still we people are waiting for KGF chapter 3. But I have a chapter 3 for you. Okay. And here the hero is bit different. Here we don't do this is, you can compare with the Salar. Okay, Salar movie. And Salar, I think hopefully all of you have watched, and there the hero is Prabhas, and that is there he has to do nothing with our Rocky Bhai. But earlier there was a speculation, no, Rocky Bhai will come. Like there's a relation between Rocky Bhai and Salar. So that kind of thing also we'll be able to see here. Here, what we'll do, basically, we'll be controlling the electromagnetic field by making some sort of the soft wavelength size metal. And throughout the, like in the upcoming chapter, we'll be looking at what are the different metal. And again, as I promised, like we'll be including few of the magnetic property to that metal to show very interesting property. Okay, so again, how it came into my life, like I was very much happy, like I was showing all my works, right, and I got some award. I was doing my PhD, I was having a very cool life, I was writing very good number of paper in by using this tin oxide, and my life was pretty cool. But all of a sudden some problem came using this tin oxide itself. That leads to me a new direction, new world itself. And what was that problem? The Raman spectra, actually. Here we can see, and I have already appreciated much about the quantum dot. Like quantum dots, it's really powerful. They are having very excellent property. They are having various application and all this thing. Already I have proposed it. But when I'm taking the Raman spectra, and this pink color or magenta color, this is the Raman spectra for the 25 nanometer particle. And here we can see all the sharp peaks. This A1G, EG, and B2G. And they are the tin oxide related peaks. But if I am taking the Raman spectra for the quantum dots, I am not getting anything. Rather, it's giving a very broad peak, and it has to do nothing actually. Like it is not the material property. Then I was really in a trouble. Then how will I explain that this is tin oxide? Because now I have claimed a very big thing using tin oxide. No, this is really great. And suddenly Raman spectra is coming and telling, no, your material is completely wrong. It is not showing any Raman spectra. Then I was in a deep trouble. Then again, the good thing is that before to us, there are lots of brilliant people, lots of brilliant scientists. They have worked enormously and they have written there lots of good paper. So that is what is really important, like literature survey. We need to do as much as literature survey we can do, so that we will be having a conceptual clarity. So one of the paper I was going through, that is in the JAP, Journal of Applied Physics, and what they claim, as I told, this smaller particle, they contain lots of defect. So this defect layer is there, and they are completely surrounding the actual tin oxide part. So the tin oxide part, or the Raman spectra of the tin oxide, is not able to come out from this defect related peak. So this D peak is sometimes I call it a danger peak, but it's a defect peak. Okay, and the actual Raman spectra is like hidden under this broad peak. So that is the problem. Then the question comes, like curiosity will obviously come, is there any technique by what we can enhance the Raman spectra? Okay, if I will be able to do that, then what I can do, this spectra can be enhanced, like whatever is there underneath this broad spectra, they can be enhanced, and I can easily tell, no, they are the Raman spectra. And luckily, few people have, like theoretically, they have shown, yeah, this is the theoretical data, and this spectra should be there in the quantum dots, but they could never. And this is one more experiment, like few people tried. This is published in 2019 in Science Advance. There come the rescuer. Okay, the plasmonic, our second hero, Pravas. P for plasmonic, P for Pravas, basically. So this is the plasmonics material. What happens, that I will explain what is plasmonics and how plasmonics can be a rescuer to enhance the Raman spectra. That will be showing in the next slide. Okay, so this is the plasmonic gallery. What generally happens, if you are shining a light on a plasmonic material, there will be an oscillation in the free electron. Okay, this electron will start oscillating at a certain frequency. But here the key role is that, like here you can like see this interaction of light with the nanostructure metal films and the nanoparticles. They will create the plasmonics. And why, if you see this structure, why it is important? Here the structure, if this is the metal, this size is lesser than the wavelength. Like the wavelength what we are dealing with, like we are generally dealing with a visible wavelength that ranges from 400 nanometer to 700 nanometer. So the nanostructure, the nanomaterial or nanometal, what you are planning to make, that should be lesser than that size. That's why in the title, I clearly mentioned that your soft wavelength metal, you are not dealing with the bigger metal. And this is how it is different than our earlier stone ages, iron ages, and all these things. Because you are not dealing with the bulk material, you are dealing with the smaller nanomaterials. And if you are signing with them with the smaller nanomaterials are signed with the wavelength, this free electron, they start oscillating, and they don't oscillate in a random frequency. Okay, there is a quanta. Okay, and that particular quanta is known as the plasma. Okay, and by this, what they do, they confine the electromagnetic wave around the surface. So earlier, in the other case, what will happen? The light will come and that will reflect back. Okay, if your material is bulk, and this kind of liberty or this kind of excellent property you may not be able to see. But if your material, if your nanostructure is of smaller size, the electromagnetic field will be confined around the surface, and that particular light will be absorbed. Means you can tell, because that when you are taking out that spectra, that light is confined here, so you will not be able to see here. So you can tell that that particular light is absorbed in the metal. Generally, that concept is really weird, right? Because metal never absorbs light because it doesn't have any band gap. But here, this is not band gap related absorption. This is the plasmonic related absorption. And if they are confining that light, what will happen? Like those who knows about the Raman spectra, why we are not able to get a very proper Raman spectra? Because they deals with the inelastic scattering. And what is the inelastic scattering? The process is very weak, so you may not be able to get a very strong signal from the Raman spectra. But if you are confining the electromagnetic light, that will enhance that particular Raman spectra. Or what I want to tell, if you want to take the like enhance the Raman spectra of the tin oxide, what you need to do, you just keep some gold nanoparticles and you just keep your material close by this. Like here, I can keep my tin oxide near to this plasmonic materials, and then I will take the Raman spectra, so that the Raman spectra of my material will be enhancing. So what are the generally what people use for this plasmonic materials? Gold, silver, and copper. And why people use gold? Because as I told, this plasmonic resonance come for the visible light for this kind of material: gold, copper, and silver, and gold. And why don't use this silver and copper? Because there is a high chance that they will get oxidized, so you'll lose your original property. And we can that's the reason generally we people use gold. And so gold is a very important plasmonic material. And here we can see there are different generation of the structure, like first generation, second generation. What do you mean by this first generation and second generation? If you're taking a single gold nanoparticle, okay, and whenever you are seeing this blue color or some different color, you can think that the electromagnetic field has been confined here. So here you can see a weak electromagnetic field has been confined. But when you are combining these two gold, you can see the confinement is increasing, because this particular junction is known as the hotspot. Okay, and in this hotspot, the electromagnetic enhancement is very high, and here the power of the electromagnetic enhancement will be very high, and there the signal enhancement also will be very high. And with that motivation, we started making some gold nanorods here. Okay, and for that, what technique we utilize, that is known as the seed mediated growth. So in this process, it is this two-step process basically. First, we prepared some seed by the interaction of the HuCl4 and ammonium hydroxide. Then later on, we made the reduction of the HuCl4 on that particular seed. Like here you can see, you can understand from this particular diagram actually. These are in the first step, we created some seed. Okay, seed will come here. And in second process, from the seed itself, you can grow different kind of like gold nanorods. So these are the different gold nanorods that have been created different using this technique. Then the question is that why I want to make these gold nanorods and not the gold nanoparticle? Because these gold nanorods, like if you are dealing with a particle, it will be absorbing only one wavelength because of this dimension. But if you are dealing with the gold nanorods, it is having two different things. One is length and one is width, and it can absorb two different wavelength. This you can see, this is known as the longitudinal wavelength, and this is known as the transverse wavelength. So this is the motivation that we should make some gold nanorods by taking this as a challenge. And using like during the seed mediated growth, you have to use there is a liberty of using various chemicals, like starting from you can play around different chemicals like HuCl4, then silver nitride and C-tape. Because what I want this peak in a very particular position, or I can vary this peak as per my requirement. And to obtain that, we did various experiments, and we could able to tune the SPR peak from different positions. Okay, and I understand this peak, spectra are really boring because they are nothing but some random lines. But what if I will tell that these all are the gold nanorods? Okay, they all are the gold nanorods with different sizes, and you can see their color is very different. And why they are very different? Because they have absorbed different wavelength. So though they are the gold, of metal, and whenever I'm telling the gold, the automatic color that will come into my mind is yellow. But here we have seen, we have created a spectra of color using the gold nanorods, and they absorb different light. Like the kind of light I want to absorb, I'll make a gold nanorods in that way. Okay, and this is a synthesis technique like what we have followed. Again, the same thing only. The ascorbic acid and CTAP and all the concentration we could, during this process also we could get some kind of dog bone structure. This is exactly looking like a dog bone. Okay, but finally we could get a better structure. That is what we are preparing for. And finally, what we are going to use, this gold nanodes, what we have used for, that's known as the surface enhanced Raman spectroscopy. And what is that process generally? Using this, you can detect the trace amount of the dye or trace amount of the color. Like if there is very small amount, like here you can see the concentration is 10 to the minus 11 molar. And it's a dye, of course, it's a test dye. Okay. Because you want to see finally what my main idea was to enhance the Raman spectra of the tin oxide, right? So before that, I was seeing that how powerful is my plasmonic material. So to test that, I have taken rhodamine 6G with very less concentration, 10 to the minus 11. Still, you could get all the spectra over here. So my material are behaving properly, but they were not enough to solve our purpose. Because 10 to the minus 11 is because the paper what I followed in the very beginning, where they tried that for tin oxide, they could go up to 10 to the minus 16 molar of R6C. So I understand that this gold nanorods is not going to help. So I changed my material. So we again prepared some silver nanorods, and that went into 10 to the minus 14, close enough. But still that was not possible. So now we try using two different gold plasmonic materials, like gold, silver, and gold. Here I want to mention that the plasmonic property of silver is much more higher than the gold. Okay, but why we can't use silver? Because there is a very high chance that they will convert into oxide. So what can I do? I can prepare a silver, then I can coat it with the gold. Then it will not it will not convert or it will not oxidize, and I can use them for the source activity. So with that plan, again, these are the plan like we did with some of the BSc student. Okay, they come like in my PhD, few BSc students were coming. So this particular work was done by one BSc student, and obviously this was a joint we were doing that together, and that is our plan to again. But our purpose was decided we wanted to prepare a better source substrate for the enhancement of the Raman spectra. And this is a beautiful structure what we have prepared, okay, by varying the different concentration of silver. And here we could go up to 10 to the power minus 16. So earlier we could go up to 10 to the minus 11, then it's improved to 10 to the minus 14. Now we are dealing with the 10 to the minus 16. But our mark was 10 to the minus 17. If I could detect up to 10 to the minus 17 rhodamine 6G, then I can go for my my real experiment. And this thing happened. This is a very accidental outcome, of course. What we are doing, we are adding silver nitrate and ammonium hydroxide. What we did, we added extra ammonium hydroxide on the silver nitrate. Then what we see, what could we see? Some kind of flake structure was floating over the solution. And out of curiosity, we took that flake structure, we collected it, and we saw under the FESM, and they were nothing but the beautiful silver net kind of structure. Okay, and as I've shown, here the concept of the hotspot will come. Like if you place or if you keep two plasmonic material nearby, here the electromagnetic confinement will be very high. Here the electromagnetic confinement will be very high, and this is the theoretical outcome. This technique is known as the FDTD, finite differential time domain calculation. Like this is the actual sample, and these two are the theoretical outcome. And we did some FDTD, and we could see that if you are taking this kind of structure, the electromagnetic confinement is very high. And experimentally also you can see this kind of confinement. This technique is known. Again, I am not giving, just I am giving the word, so that those whoever are interested, they can go and search what are this technique. This is known as the photoluminescence. From here also you can see the plasmonic importance of your material. And there is also, this is a paper, this is not our work. They did a similar structure, and this is the kind of the CL spectra they got, and they could publish it in the Nano letter. And this is our data, almost exactly same. Okay, so this is our data. And using this, we could go up to 10 to the power minus 18. Here we can see a small spectra. Our initial aim was to make something of 10 to the minus 17, but because of this beautiful structure, we could detect up to the 10 to the power minus 18. So our hero for the third chapter is ready. And as I told, what was my aim? If you don't forget yet, like the main aim was to see the hidden spectra from the quantum dot. Okay, so now my job was very easy. What I did, I took the silver nanonets, and above that I dispersed some of the quantum dots and bigger particle, of course. And I wanted to see how the spectra is changing. And here we can see a very small thing was coming out from this particular thing. Okay, so the hidden spectra was finally enhanced using the silver. Okay, and this work was also published in the SS Applied Nanometals. And to cross verify that, again we did some other experiment, that is high pressure experiment, because as you know, like if we have done Raman spectra, if you give higher pressure, what will happen? This particular peak will shift to the higher side. So this is what was happening. So if I am giving to the higher pressure, the peak was shifting to the higher side. That also one more proof that the Raman allowed peaks are present in the tin oxide quantum dots. However, they could not be visible earlier because of the defect side. So we have find out the hidden peak using two different techniques. One is by the plasmonic things, and second one is the higher pressure. But thank you to this problem, basically because of that we could extend, or we could enter to the field of the plasmonic. But here, like plasmonic doesn't stop us surprising. And here I will not explain it much, because again it will be so much of things. Here, like as an extension of this work, we did also some TERS. This is known as the tip enhanced Raman spectroscopy. Okay, in that what happens, generally we can do the search using the AFM tip, and we collect the spectra. And some here what happens, generally the mutual exclusion principle was broken. Means those who knows about the mutual exclusion principle, the Raman spectra and IR spectra, they could not be seen simultaneously. Okay, unless and until there is some perturbation or there is a loss of the center of symmetry. And here what we could see, this is the IR picture at 6:15, and that spectra was coming out when we were doing the TERS, okay, tip enhanced Raman spectroscopy. And that is because of the mutual exclusion principle in the presence of the local plasmonic structure. And there is a very important and very interesting theory, like those who have started using this quantum mechanics and all these things, they could understand this part. Here basically what you are doing, you are perturbing your material by keeping it in a electromagnetic field, and you do just some bracket kind of mathematics. And if you don't want to go to the complexity of this calculation, the take-home advice is again that this I2 stand for the intensity of the IR peak, and I1 stand for the intensity of the Raman peak, and that is directly proportional to the electromagnetic field gradient. So because of that, the I2 stand for the IR peak, that could be enhanced when you are doing the Raman spectra. So finally, the problem was solved, it seems. And with that, of course, we didn't stop. So we got the importance of the plasmonic, why it is really interesting. Then we started making very beautiful structure. Then we went for different kind of alloy. So this is basically a gold germanium alloy. You can see it's a kind of gold germanium core cell structure. Okay, and again we did some CL, cathodoluminescence and cathodoluminescence imaging, and again we continue doing SARS. Okay, because still we can see this narrow down to a single particle hybrid plasmonic effect. This is a single particle. It's of course it's of a micron size. Okay, but here we saw this plasmonic activity, like theoretically as well as experimentally using the cathodoluminescence. Then the question, one more thing generally come, as I told, this electron got excited, okay, when you are shining light on the metal. Then what, next what? How the electron calm down or how the electron cool down? They are the concept of hot electron comes, because now the electrons are really energetic and they need to be collected. If you can collect that hot electron, what you can do? You can do the catalysis experimentation. Okay, so that is the beauty of the hot electron, and nowadays this really a hot topic, especially in the field of the catalysis. So what they are trying, they are exciting the hot electron and they are trying to collect it before it could recombine. And how do you collect that? They have to make a suitable partner, like it can be a semiconductor or something. They will make a metal and semiconductor structure so that a hot electron will be created and they will slowly transfer to the metal oxide or some semiconductor. and there this hot electron can do some sort of catalysis study. If you see that you can understand. Okay, and it's other way around actually. This is the plasmonic things. Yeah, this one you can understand actually. The hot electron is created here and it is transferring to the semiconductor, and that is later on available for your catalysis reaction. So what is, again, what is the case here? The electron recombination is very quick here. So this hot electron detection as well as utilization both are challenging. And if I will mention, they happens in the like femtoscale. They are very quick, very quickly they will recombining. And all of you know, because of this kind of scale, only the last year, like this year, Nobel Prize goes for this kind of work. Okay, because they want to see this short, small phenomena. So this detection as well as like collection, both are really challenging, and that can be, as I told, that can happen, or that we can realize by making a proper partnership between a metal oxide and plasmonic material. So that is also, these are the few slides I want to show just to give a flavor like how it importance. So with the ongoing journey, what we are planning, we are making beautiful titanium oxide. This is a TiO2, and we are decorating them on different kind of plasmonics. Basically, this is the structure. Actually, first of all, we are synthesizing our TiO2 using this hydrothermal growth technique. Then they are decorated with gold using thermal nanostructure, thermal evaporation. We did some basic characterization like your UV visible, PL, and Raman study. Then we went for the catalysis work. Okay, so here we can see this is the spectra from the dye, and slowly they are going down. Okay, because this is happening because of your catalysis experimentation. Okay, and here also I'm not mentioning, there are so many theory also, because how then the question is very clear, how you know the electron has been transferring from here to here or here to here. Okay, so to explain that again, we take the help of the resonance of the TiO2, because whenever there is electron transfer from your metal to the metal oxide, the Raman spectra will change. This is the earlier spectra, and if this is the gold decorated, here you can see Ta0 means there is no gold. 4 stand for the 4 nanometer gold. Actually, we have decorated with them 4 nanometer gold, and in that way, what is happening? The Raman spectra of the TiO2 is completely changing. So it is basically asymmetric structure, and from that you can connect them with the phenoresonance, and that is a direct proof of the transfer of the hot electron from gold to TiO2. These are little bit of theoretical thing. Okay, but again, for the sake of complexity, and I just want to tell so that if anyone is interested, they can go and search in that direction. And one more important thing, like from Stokes and anti-Stokes Raman spectra, you can measure the temperature also, because whenever there is a gold, that creates some localized heating, and that localized heating is also really helpful for your catalysis experiment. This also you can see, like when you are having TF4 or the material with the 4 nanometer gold, from this anti-Stokes thermometry, we could finalize that there is a localized temperature enhancement, and that is really good for the catalysis. So for this nanometal, you don't have to have a physical thermometer and go and check the temperature around there. Just you have to do this Raman spectroscopy. You have to collect the Stokes spectra and anti-Stokes spectra. You just compare their respective intensity, Stokes intensity, anti-Stokes intensity, and from there you can calculate the temperature basically. And again, nowadays, like all the people are working in 2D materials, so we thought of extending our work to the 2D materials also. We synthesize using CVD some TiAc2, this is titanium selenide, and on that, using the similar technique, we decorated gold nanoparticles, and we could show a very beautiful SAW structure, and as well as this catalysis property. Okay, so in conclusion, what I will tell, like we had a problem with tin oxide, and when we were solving that, we could create a very good and very beautiful plasmonic gallery. Okay, this was not our aim actually, and this all the thing came accidentally, and most of the work, like when I was doing PhD, my work was to deal with tin oxide, and during this gallery was created mostly during the summer vacation, because summer vacation, various student will come, then I will take little rest from tin oxide, and we will explore a new world. It's the plasmonic world, and we are creating basically this plasmonic gallery. Okay, and so this is the end of the movie, but don't go now, because if people Marvel fan, then after every movie there is a end credit scene. Okay, what's going to happen next? So this is the end credit scene. Now what we are working on. Okay, so now what we are doing, we are inserting magnetic material in the plasmonic material. Here, if you can see this red color is basically your nickel. Okay, and the sandwich, the green color, that is now the gold. Now the plasmonic material is sandwiched in the magnetic material. Here I want to see how, because as you know, this electromagnetic, we call this the electromagnetic wave. So electromagnetic wave may behave differently in the presence of the magnetic field. Okay, and the confinement maybe will be entirely different. And again, if this is magnetic, your once your job is over, you can take an external magnet and you can collect your sample back. So those are the idea now what we are having. And like emerging, this also emerging field that is nowadays coming up, that is your magnetoplasmonic, how the plasmon is changing in the presence of magnetism. So that is our next target, and that is what I can tell the extended plasmonic gallery. Okay, so these are our group. Like here, I did my PhD. Most of this Raman, whatever I've told, and KPFM and AFM, it's done by here. All this instrument. And here, I just want to mention one thing. I have heard my instrument whispering. Like that, all can agree. Like those who do experiment, they talk with their experiment instrument basically. If you go to an instrument, you can, if you just show your ear, then you can slowly listen some sound is coming from, it is telling good morning, good evening. So that much emotion, especially I am having with my instrument. Okay, so this is the KPFM and AFM. This is a Raman spectra that generally I was using for my experimentation. Then I came to Niger. Here I was working as this cancer cell and all. We are detecting cancer cell using the Raman spectra. That's a German based project. And this the, as I shown, this thermal evaporation and sputtering. This is the thermal sputtering and thermal evaporation. This is the instrument mostly I was using. And here I think those students are not there, that project student. This is basically, this was our group, and this is the group belongs to the Niger. Okay, and this TiO2 work was a collaborative work with Subhasri, I think it is C, and the 2D work I was continuing with Utkalika. So they are also like the director or assistant, of course, director, assistant director, whatever, of this movie. Okay, and currently I'm working here. This is our classroom, and I think a few of the students are also present. I was seeing their name during this presentation. This is our MSc student actually, and they're working good. Let's see. And this is the BSc student, and hopefully they will be joining this AIP, and they will getting, they will be like, they will get to know more about the brilliant mind those are present, and they will slowly they will get introduced. And this is my team basically. Okay, so and we call us Avengers basically. Okay, so you can see there's a great similarity between this picture and this picture. Yeah, thank you, sir.
Thank you so much, sir, for a very amazing and extraordinary work and talking about like movie kind of thing. So I think just I just add something for your lecture or for your talk. So teacher should always including kind of a story in that particular theory class. So student have understand very deeply and correlate with that particular phenomena and all this. So it is a very amazing lecture today. Thank you so much again, sir. And now the session is open for the question answer. So please, if you have any question regarding this kind of talk, yes, you can, sir, please.
Yeah, thank you. So I'm Yugen Kulkarni from Maharashtra, and I'm also just started working in catalysis. My
Okay.
material is Cu2O and
Uh-huh.
MnCO4. So my question is, can I guess before starting the experiment on which dyes my material can work better?
Yeah, that you can always do, because for that, first of all, you have to see, we have to understand the basic principle that how the catalysis is happening. Okay, so there are two kind of mechanism. First one, in first cases, what happens? You are exciting the electron in your material itself, in your
Right,
like the Cu2O. You are working basically in the heterostructure, right?
right.
Yeah, so the electron and hole pair will be created. So basically, you have to utilize that particular uh, wavelength. Okay, and later on that will go and degrade your dye. There is one more mechanism also. In that case, what happens? You generally excite your dye. from the homolumo, like they are having
Right.
homo condition and lomo condition, and that also can be done. And
Right.
this catalysis also one more important factor, that is the adsorption. Okay,
Right.
how better it is absorbing on your material, and theoretically it's predicting, like theoretically you can predict. Okay, that is obviously you can predict, but I am very sure that they will not be matching with your experiment. Okay,
Okay.
because these experimental things are very much different than the theoretical. Like
Right.
if you're going, that is what I believe. Like we are going from theory to experiment. Sorry, if you're going from experiment to theory, that is uh, typically easier. But if you're coming from theory to experiment, that's a bit difficult, because in the real life, in the experimental, there are lots of parameter, and
Yeah.
till now we cannot like simulate all the things. Obviously we are dealing with this machine learning and deep learning and all these things, but exactly simulating your material theoretically is bit difficult. So I guess you have to go for the literature study, obviously, and if I like intuitively you want to go, then you have to do using this trial and error method basically. And this dye, like band gap and all, you can choose as per your material, like what color
Right.
like tin oxide that may not work in the visible light, because the band gap is 3.6. So I
Right.
have to use the UV light for a better catalysis.
Mm. Yes. Sir, there is one more thing I observed.
Yeah.
For methylene blue,
Yeah.
without catalyst, it shows decolorization.
Yeah,
So,
yeah, yeah, yeah. Yeah, yeah. For our group, please, like, you can see, like, oh, recently we have published one more work in that direction. That's called the adsorption, actually. Okay.
okay.
So that is not the photocatalysis, that is the only catalysis. Because
Yes.
as I told, your surface is very much complex and very complex, that contain lots of dangling bond. Okay. Our
Okay.
material contains lot of dangling bond, and they adsorb the dye. And you might have seen that something is what you can call settling down in the bottom, and that powder will be colorful, a
No,
blue
sir.
color or something,
No,
right?
I'm talking about without using catalyst. In presence of light,
Without, ha 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 ha.
without
Uh,
catalyst.
uh, okay, okay, I understand. So what is the light you are using for that?
Solar light, natural sunlight.
And what is the dye?
Methylene blue.
Okay, then I guess you need to check with your dye, because I don't think, but if you, it is a solar light, right? It contains UV in it.
Yes, yes, yes.
Ah, that's the reason. Because if you put UV on methylene blue, they will degrade. As I told, there are two mechanisms, right? Electron may
Ah,
go from your material to dye, and the second mechanism, in your case, the second mechanism is happening. The
right.
color, like it itself, it will take the UV
Dye itself
visible.
is absorbing light. Right.
Yeah, yeah, it itself is absorbing and degrading.
Yeah.
If you somehow you can put a filter in that, if you just cut out the UV light, okay, and you
Okay.
check, it will not happen. Or
Ah,
one thing also you can do is just take your dye and keep in the solar light outside.
right.
Okay, there UV part will not be there, so you may not see that kind of thing. UV
Right.
will degrade your methylene blue. That is very sure. Only
Okay.
UV.
Okay. Okay. Thank you, sir.
So, sir, I have a, question. So you have shown like a homo-lumo kind of thing. Okay,
Yeah.
so I'm I'm working on that particular homolumo energies and all this. So how can we use, or how can we apply in this work for of the homolumo?
Yeah, of course. It's just see. Means again, the depends on the what kind of mechanism you are proposing. Okay, means in one of the work I was showing the degradation of methylene blue using solar light and using tin oxide. Okay, so I was using this tin oxide, and tin oxide will not absorb any solar light because the band gap is 3.6. Okay, so I had to go in the other way. I had to excite my dye. Okay, so there I include the concept of the homolumo, the light, the electron, the dye excited to the higher state, and it again came back to the ground state by transferring few of the electron to the tin oxide. Okay,
Okay, sir.
uh, you got the answer?
Yes, sir. Yes, absolutely.
Okay. Yeah, also you can like that is one of the work we have published in chemosphere. Okay, there's a like composite of tin oxide and graphene oxide. You please see that. Okay, I think you will get the answer. Means there we have explained this homolumo interaction with the dye, with the catalysis material. Okay.
Sure, sir.
Yeah.
Thank you so much, Binay sir, for
Thank you.
nice talk. And I'm really enjoyed this lecture. I have one small questions related to basic. That whenever electron coming from excited state to that ground state, and they are emitting some kind of photons, why that photon is not capable to absorb in that material? Please throw on light.
Sorry, sir, means you are telling that that light itself will be absorbed in that particular thing?
In you can say in KGF chapter 1. In chapter 1 you were
Okay.
saying that, yeah, this one slide.
Yeah, yeah.
There is the emission of some kind of light when that electron comes from a higher energy state to lower energy state. So
Mhm.
why that energy is not going to absorb in that material? What is the reason behind this? Yeah, please.
Okay, means
Why we are getting photoluminescence? Why that energy is not able to absorb in that material?
yeah, yeah, okay, I got your question. Yeah, this photoluminescence again, it deals with different lifetime. Okay, because there are different trap state. So sometimes it got trapped. Like there is two kind of things. One is radiative recombination, one is non-radiative recombination. Okay, so
Okay.
it is not like that all the light will radiate. Of course, there are few lights that will be non-radiating actually. Okay, if there are so many trap state and all this state, all the light, like whatever, all the recombination is not at all possible. The few lights will be trapped inside the trap, trap state actually. So it is very much possible that few lights will be trapped and few lights will be coming out. It's not like all of the light will come out or all of the this emission will come out. There is a high chance and high probability. So that's why all the materials are not luminescent. Okay, so if they contain lots of trap state, lots of defect state, then they will get trapped over there. And before that, if their lifetime is really good, like if we'll do the lifetime measurement and all, if their lifetime is really short, before they could trap, they will recombine, and there we can see the PL photoluminescence. And I think this luminescence also different kind of right, like photoluminescence, phosphorescence, and all. There is a huge like 4 5 type, and that is they are divided in terms of their lifetime again. Okay, so based on their lifetime we can tell whether they will be trapped or they will combine, they will like they will be radiative or non-radiative. And they also, there is few phenomena, they act as the non-radiative transition, they got absorbed in the material itself. That is very much possible as per my knowledge actually.
Okay, sir. Thank you. How you have calculated this band structure? Either experimental, there is a experimental method to calculate this band structure.
Yeah, yeah, yeah. Experimental method we can do using UV visible. Simple UV. Here I have not shown this for quantum dots. We got around 4.2. Again, that is because of this quantum confinement effect. Whereas for this bulk, not bulk exactly, like 25 nanometer and all, they were to this 3.6 nanometer. That's one of the technique, and one that is basically when we talk about the band gap. This is what kind of band gap I am talking about. That is, one is optical band gap, second one is electronic band gap. Okay, so this optical band gap, as I am talking about lots of optical applications, so I gave the information about UV visible. But if you are dealing with this electronics related application, then you can think about this XS spectra, and from there, from UPS basically, XS and VBS. XS will give information about the conduction band, and VBS will give the information about the valence band. You just combine both of them, and you will be able to get the exact electronic band spectrum experimentally.
Okay, thank you so much. So you have
Uh,
already ready for KGF 4. You have already launched the KGF
Yeah,
3.
yeah, yeah, yeah. We are
Yeah,
always in a mission actually. And
yeah. So
now the good thing is that I am having some good students, and hopefully they will be the real hero. Now I'm old and it's time to retire.
Actually,
thank you
I
so
have
much.
one more question from my end.
Yeah,
Uh, you have studied about the detection of a gas using the photo PL spectra
yeah, yeah.
on the website. So I would like to know about that. How exactly you modified the instrument
Environment.
in order to measure the in order to sense the different gases.
Yeah, this one. Yeah, yeah. This is
Yeah,
a
yeah, yeah.
very interesting question, and yeah, that is the key point of this work. The instrument is looking sophisticated, but it's not that sophisticated. Okay, we have designed it using a cuvette. Okay, a visible cuvette. But this system, this was really important for this because we have to have a airtight kind of thing, and the main challenge was is that we need to keep this whole setup under the Raman spectrum. Okay, and this ammonia, basically I did with the ammonia and alcohol and ethanol and methanol and all these things, and they all are the VOC. Okay, they are the volatile organic compound. So what I was doing, I was just keeping a bowl over here, a small bowl of micron size, and I was keeping few drop of the material, and that can be like if you see the formula, that's why I've given here. There's a term V. V stand for the volume. Okay, and from there you can convert, and if you do this calculation, then that can be converted into ppm. Okay, ki how much ppm is going based on
Is
this.
this formula static
Sorry.
formula, static dynamic formula? Is it this
This
formula?
is a static actually because
Okay.
as I told, I was keeping very small amount of VOC, right? So they were completely evaporated. So now my chamber is complete with that volume of material. So I can tell that is of this much ppm. Okay. Then next I had to go with this nitrogen. Okay. So again they will go out from this outlet. Again I'll put one more concentration. But as I told, this was our initial experiment. Now we are having a very well-equipped setup. Now we have connected with Mossbauer MFC and all. Okay, so that system is developed now. This is like 2 years backward. So this is what our initial model. And now we are connecting with MFC, and we are seeing even now we are combining this resistive and optical together and giving some heat also, and we are connecting with thermocouple, and we are checking the temperature stage, like temperature of the stage and all. Now it is modified, but the work I was showing when the system was in the very rudimentary state and using a simple cuvette.
Well, here, laser light is incident on the sample,
Yeah,
and what you mean is that all this experiment is performed under using the Raman setup.
exactly. Renisa Raman setup actually.
Okay, fine, fine. Actually, I also work in the gas sensor, but basically, as I don't have such facility, I work on only in chemi resistance only.
Yeah, that also our group work chemi resistive mostly. This tin oxide is it's very well known gas resistive sensor. So I thought of going little out from that,
Actually,
and I tried.
optical sensing is far better as compared to the chemi
Resistive
resistive
sensor.
sensor because
Yeah,
the
yeah, yeah.
sensitivity is very high. Another one.
Exactly, exactly.
Second
Sensitivity
one
and
is the,
selectivity, especially I
yeah,
found they are really great actually.
and not only that, it can be reproduced multiple times. Means similar data
Exactly,
can be.
exactly.
So
Yes, yes, yes.
I got it,
Yeah,
but with
that is
certain
because
limitations, I'm
in
not able
resistive sensing, that is the like as you are working in that field, the main problem what I found is the contact problem. Like how precisely you try, you never get the similar contact in the second time. Your contact
Yeah,
will be
yeah,
very
yeah,
different, your data will be exactly different.
yeah, yeah,
So
yeah. That's one
reproducibility
of
is
the
a huge
biggest
challenge
issue.
actually. Yeah,
And
yeah.
in that case,
So
we
I
used
faced.
to have the thermal physical vapor deposition, and we
Yes.
specifically make that contact area. And for that, we prepare one special mask, and we used to
Okay.
take the contact it with that. Okay,
Yeah,
thank
that
you.
also we also do, but again we need to disperse your material, right? Using spin coating or something. Sometimes that also I don't know how like precisely we can reproduce. So those problems generally I faced during my experimentation.
Yeah, but in that case, we have to sometimes we used to use some binding agents that which are
Mm-hmm.
non-conducting and in
Yeah,
a
yeah.
fixed proportion in order to produce the same amount of result. But still, there
Mhm.
is a experimental error in measuring the resistance. Sometimes
Uh,
it give more resistance in the same ppm, which is already come across by everyone.
exactly. Yeah. Yes.
Thank you.
Okay. Thank you, sir.
So there are also two questions in the chat box. So first one is the what is the meaning of EELS?
Okay.
From the Dharmendra Singh.
Yeah, EELS is a technique that is known as the electron energy loss spectroscopy. Okay, so mostly they comes with the TM because there you are probing electron, right? So there you can see the structure as well as you can get the structural this spectroscopic data, like how much energy is lost by the electron. From there you can get this different kind of peak, this SnO2, so tin related, oxygen K peak, tin M peak, all this information you can get using the electron energy loss spectra for the metal oxide. And one more thing I want to add is EELS is also equally important for the plasmonic experiments. Generally, if you want to see what exactly happening in the nanostructure, nano scale plasmonic material, you can do EELS on the gold nanoparticles and you can see very beautiful plasmonic structure, what generally you are getting in the UV visible. But in UV visible, you have to take a cubate and you are getting the information from the whole cubate, right? But if you want to know what exactly happening at the surface of the gold nanors very precisely, then you can do EELS, electron energy loss spectroscopy.
Okay, and one other question from the Jayanta De. So Bohr's excitation energy greater than quantum dot. So what is the meaning of that?
This is also a very interesting question. Just see, here I want to, okay, I'll explain little bit of basics. Suppose you are swimming in two different river. Okay, one river is full of water and second river is full of oil. Then what will tell? Your speed will be more in water, right? So what you can tell that your mass is less than less in water and more in oil. But that is not true. Your mass is very same, but the velocity will be different. So there it comes the concept of the your effective mass. Okay. Similarly, the mass of the electron is not same in different material. Like the mass of the electron may not be same in your tin oxide and it is and then the zinc oxide. Both are different. So this is the first thing what I want to convey. Then the second thing is important. That is called as the exciton. Okay, whenever you are shining a light, what will happen? One electron and hole will be created. And generally we'll tell them, oh, okay, electron is different and hole is different. No, they are not. They are still bound. Okay, it's just like nucleus and one electron. Electron is connected to the nucleus, right? So there in a hydrogen atom. And from there you calculate the Bohr radius. Similarly, the same thing you can think about here. The hole and the electron, that's a single structure. And that is called as the exciton. Okay, and that exciton has a particular radius, the distance or the length. Okay, that length is known as the Bohr exciton radius for a particular material because that depends on the mass of the electron and mass of the hole. That's why I've given the first example. The mass of the electron and the mass of the hole is different in different material. So if you calculate the Bohr excitation radius for tin oxide, zinc oxide, they will be different. Okay, and if we calculate the Bohr excitation radius for tin oxide, it is 2.7 nanometer. Okay, so if you are able to make anything lesser than 2.7 nanometer, then you will see a quantum confinement effect. Okay, that's the 1D box problem, 2D box problem, those kind of problem we have done, right? So if not the electron and hole, they will not show any classical properties. Now they will be very much discrete. Like whenever I'm telling quantum, the energy level will be discrete. Okay, and lots of other quantum phenomena. The first property, like that is not the exact thing, but for simplicity, generally this is the definition I give. Like you might have solved this energy box problem, right? Energy equal to n square h square pi square by 2 ml square. The L stand for the length. But if you are making the length small, then what happens? The energy will increase. So that is what, if you are coming to the quantum confinement region, the band gap increases actually. Okay, so generally the band gap of tin oxide is 3.6. But if you are making something lesser than 3.6, making something lesser than the Bohr excitation radius, the band gap increases from 3.6 to 4.2 and 4.4. So that is the very easy symbol or easy sign that you can tell there your material is obtained quantum confinement.
Hello,
Okay.
can I ask?
Yeah. Yes.
Yeah,
Yes, please.
yeah, please.
Okay, so I am from nuclear physics background. So I just want to know what is quantum dot. If you can explain what is actually this features of quantum dots.
Yeah, of course. This is what only I was explaining now. Okay, so just see, we are very much obsessed with this nano, right? So anything that is in the nanometer scale, they excite us much. But all the nanometers or nano dots are not the quantum dots. Okay, so that is what I was explaining now. That is related to the Bohr excitation radius. Okay, every material is having some sort of the Bohr excitation radius. For tin oxide, it is 2.7 nanometer. And if I'm able to make some tin oxide lesser than 2.7 nanometer, the bulk property of the tin oxide will be completely lost. Okay, it will not show the same property what it was showing when it was 8 nanometer, 10 nanometer. Though it is in nanometer scale, it was showing some bulk property. The confinement, the electron and hole, they are not free to move because they are now confined. Then you of course know the properties of this 1D potential box. There the properties entirely different, right? The band gap and all. So those kind of interesting characteristics you will be able to see from the quantum dots, and that is in application term, in term of application, by taking a single material, you can span different wavelength, different band gap, and that is the like heart of your solar cell, quantum dot solar
So
cell. They will be using a single material, single quantum dots, but by changing the size, they will be able to absorb various band gap, and they will span the whole spectra of the solar line,
so
solar spectrum.
you define the quantum dot, the system of hole and electron hole pair. You define as quantum dot, right?
No, electron and hole pair, they are known as the exciter.
Okay.
They are known as the exciter.
Okay. So can we observe this? I mean, in SEM or any other instrument, can we observe these quantum dots?
Yeah. I will show you. This is, you can see. Same. It is again. That depends on the material property. The beauty of the carbon quantum dot is that the Bohr exciton radius is, I think, it is theoretically infinity. So anything you can make in dot form carbon, that is a carbon quantum dot.
I mean, what are
In
the characteristics? How you say that these are the quantum dots?
Yeah. Just see. This is the tin oxide that I have taken from TEM image basically.
Okay.
This transmission electron microscope, and the particle size was around 2.2 nanometer, 2.3 nanometer. Okay, so I can tell this is a quantum dot is 2.3 nanometer. Okay, this is the TM images. So
So
yeah,
from this intensity versus degree, I mean theta graph.
no, this is XID. I am showing this image. Okay,
Okay.
this black
Okay.
color one.
Mhm.
This is the particle size you can see, and
Okay.
this is
Okay. From the size only.
exactly. And again, as I told, from UV visible. UV visible is a one more conformative state. If your band gap is increasing,
Mhm.
okay, then you can tell there is a quantum confinement effect.
Okay. If so, you limit this at to this size 2.3. Is there any? I mean, theoretical limitation? How do you define that it should be quantum dot, or if it is higher than this size, then it is not quantum dot?
There is a
How can you?
formula actually, as I
Okay.
told, that is strongly related to the mass of the electron and mass of the hole.
Mhm.
Okay, so if you calculate again, that's why I was giving the earlier example, the effective mass. Okay, you have to calculate the effective mass of the electron in tin oxide, effective mass of the hole in the tin oxide, and put in the formula. Then
Mhm.
you'll get a value. Okay,
Okay.
and the value for the tin oxide will come, it is around 2.7
Mm.
nanometer.
Okay.
If you take some other material, the value will be 4 nanometer, 5 nanometer. And if you are able to make something lesser than that, that's a quantum dot.
Okay. So material wise, that will be. I mean, size will be different, right?
Definitely, it varies material to material.
Okay. Is that anything has to do qubit with qubit? No.
Yeah, I understand actually. Means you want to correlate this with the quantum computation, right?
Yeah,
That
I
is
just terms are interesting, so I just want to know.
Yeah, that's a very interesting thing again because mostly they utilize this luminescence property. That is also one of the plan I was planning to present, but again I thought that will be too means this luminescence property they will be using. Again, that is connected to the plasmonics.
Mhm.
They will be connect this luminescence property. They will be using some kind of data and qubit. There's a work very. I think you can search. There's a group in IIT Bhubaneswar. His name is Rajan Jha. Okay,
Okay.
because recently I've started working, like I've started reading regarding this.
Mhm.
So you please search few paper from their group. Okay,
Okay.
his name is Rajan Jha. They are using this quantum dots for qubit and quantum computation and all. Okay,
Okay.
that's a very interesting work actually.
Okay. Okay. Thank you. Thank you.
Yeah.
Okay, thank you once again, sir, from the delivering a very interesting and amazing lecture for the uh, for the research scholar and all this. Thank you so much, sir.
Thank you so
I would
much.
I would also like to add physics. Yeah. So thank you so much, Dr. Binay. It was very insightful and very wonderful talk. I think most of the talks we had in this is the first time we have talk on nanoscience or plasmonics. Earlier then we have other talks, but this is the first time we have, and it was very exciting. I hope like our participants would have gained much knowledge from this thing. So it's very wonderful to have you in our team. So as most of yeah, so it's like we have tradition to have group photograph. So please, everybody, if you can switch on their camera, so then we will have a group photo. Everyone, please switch on your camera. Yeah. Then please take some snapshots.
Okay.
Yeah. Thank you, everyone. Thank you, I guess. Yes, Sanjay sir. Over to you.
Yeah. Thank you, Vinay sir, for accepting our invitation and delivering a wonderful talk on this AIP platform. We are really very grateful to you and for joining our community. Yeah, thank you so much, sir.
So, Dr. Vinay, if you have some time, so after this we have some proposal by Dr. Shuman Dev. So he has proposed a mentorship program as you are in the team. So we would like to have your comments on that also. So all the non-members, AIP non-members, they can leave the chat, and all the AIP members are requested to be there so that we can have a